Hello. Let's talk about summation notation in the world of mathematics. I've written an abstract sum on the screen today, and we're going to do something a little bit more concrete in a bit here. But I just wanted to talk about the pieces of summation notation and how they let me concisely express that I need to add up a bunch of things, which is a real win. How do we know that I'm doing a sum right here? Well, this symbol right here is a sigma, and a sigma is Greek for S. So the name of this symbol is sigma, and it's a Greek S. Anytime you see a restaurant use it as an E, you can condescend to them at least a little bit and be like, no, that's an S. And I would urge you to do that, a little bit of condescension. Okay, so we know it's a sum because I'm doing, because I have sigma right here, and S was chosen because the word is like S for sum, right? Okay. This thing right here, this J, is what we call the index or the subscripting variable. And it's the thing that I'm going to look for in my expression over here to know what I'm supposed to do and what I'm supposed to do. Okay, so then M and N are M and N indicate the range of the index. Okay, M and N indicate the range of the index. They say how far am I supposed to go. I start at M and I end at N, and it includes, in the world of mathematics, both M and N. Okay, so it includes both of them. If you're doing programming, you have to be careful as far as whether you're including the top one or not, which is not really a discussion for us because we're doing mathematical summation notation, and we're not doing like Python or C++ right now. The last piece of this is this thing right here, and those are the terms that I'm summing, and these are the things that we're going to add up. Okay, so we're going to add those things up. So how about I let this thing equal a sum? So let's go S equals. What do we do when I actually compute S? Well, I'm going to go S equals A sub M plus A sub M plus 1. I'm stepping by 1. There are other notations that let me step by numbers other than 1, but we're going to keep adding 1 to the subscript every time, plus A sub M plus, you guessed it, 2, plus, now because I don't have concrete values for M or N, I have to be generic. So when I get close to N, I'm going to start writing them. I'm going to go A sub N minus 2, A sub N minus 1, and then finally A sub N. And I add them all up. So we as mathematicians believe that, that this is more concise than this, particularly if M and N were really far apart. I'd have to draw a lot of things, a lot of symbols in order to make it happen if I were to write down the actual sum. And I, like dot, kind of gives the picture, but there's a lot of power in the summation notation that lets me express far more complicated things than I can if I just always have to use dot. So we're not so into dot. Okay. So abstractly speaking, sums look like that. And so we're just looking into some list of values A sub j. And this doesn't tell us what we're supposed to do in order to produce those values. And so I wanted to speak a bit more concretely and write up a contrasting one that actually tells me what to do. So this one is abstract in the sense that it doesn't tell me what I'm supposed to do with, it doesn't tell me where A sub j comes from, right? Just go get A sub j, and we're not telling you how I'm supposed to do that. So let's instead write something a bit more concretely. Let's go the sum from, let's go from j equals, let's go from m to n. And now let's operate on j itself. So let's use j as an expression inside this thing. Let's go j, and I'll put it in the same color to indicate that it's that thing. So I'm going to go j, and what do we want to do with it? Let's just square them. So this one is less abstract, because I actually have a formula right here for how to use j, right? So in this case, I would say that a sub j is equal to j squared. Okay, so in the less abstract ones like this, we'll actually have a formula for what to do with our j. So what do I do with it? So for example, if I were to take the sum from j equals minus 2 to 2 of j squared. Maybe you want my dots, fine. Then what do? Well, first j is minus 2. And I square it, because that's what I do with j, plus minus 1 squared plus 0 squared plus 1 squared plus 2 squared. And I add them all up, and I'm going to get, let's see here, 4 plus 1 plus 0 plus 1 plus 2. Nope, plus 4 is equal to 10. Okay, so some of them that are less abstract than this one here actually tell you what to do with your j. There's kind of another slightly different world, which we're going to use in the world of Riemann sums, and I wanted to write one of those down for you also before we call this video done. So I'm going to take the sum from, I'm still going to be summing using, say, j equals, let's go from m to n. So we're not getting particular on those right yet. And let's instead put f of in here. Let's take f of and say x sub j. So this is kind of interesting. So I'm doing some function f to some x's, but in this formula right here, it doesn't say where x's are. So this is kind of similar to this thing over here. This didn't tell me where a sub j came from. Just go get the jth a and then add it up in the sum. This one here says go get the jth x and add them up in the sum after applying the function f to those x's. So coupled with this, I must also have a table somewhere, right? I must also have a table of x sub j's and say, I'm going to redo that. I would have a table of, say, j values, and then I would have x sub j values. So j would be like 0, 1, 2, 3, 4, and x sub j, say, is minus 1, minus 0.75, minus 0.5, minus 0.25, 0. Okay, so now if j were to run from like 0 to 4, I would go get those 4 x values from this table. So this thing right here, you gotta know where to go get this. You got to go get that x of j value from somewhere, and then you're going to apply f to the corresponding x value. And then you add them up. And there are convenient ways of doing this in terms of tables, and I'm going to explore that with you in another video. Our point on this one was that summation notation is a powerful way of expressing the addition of many, many numbers, an arbitrary number of numbers, in a compact way. Sometimes we say, go look them up in a table somewhere. Sometimes we're like, here's what you do with j itself. We're going to do some action to j itself. And here we're saying, apply the function x to some x values that you go get from a table. So you'll get it from a table, and then you apply f to it, and then you add those things up. There are a number of other ways that we can improve upon this notation that let us work over, like I said, non-one stepping, so we're not adding one every time. We can add something, or we can index over some other set besides the integers from m to n. And that's all subjects for other videos. But I just want to say thank you so much for playing with summation notation with me today, and happy integration. Bye.